Crash Course Instrumentation, Episode 47. Too much current, too much danger. Intro: wires don't just carry current, they carry risk. And when you push them too hard, they push back with heat. In this episode, we're kicking off our new Overcurrent Protection series by answering a simple but critical question. Why do we need to protect wires at all? The answer? Because in most cases, overcurrent protection is there to protect the wiring, not the load. Wire insulation melts, arcs form, and fires ignite when conductors are overloaded. Loads like motors or appliances may fail, but it's the wiring in walls, conduits, and panels that's often the real fire starter. Act 1. Why overcurrent matters. Anytime current flows through resistance, energy gets converted into heat. This is known as Joule's law, and it applies to every wire in every circuit. Power L current squared times resistance, or power L I2R. That means as current increases, power loss increases exponentially. If you double the current in a conductor, the heat produced goes up by a factor of 4. Triple the current? The heat output increases 9-fold. This heating isn't always visible. It can be happening inside conduit, behind walls, or in equipment panels. And when enough heat builds up, it doesn't just damage the wiring, it can ignite nearby materials. That's why overcurrent protection is a safety issue, not just a circuit performance issue. Act 2. Real-world conductor heating. Every conductor, even copper, has some resistance. The longer or thinner the wire, the higher the resistance. And the more current flows through it, the more heat it generates. In free air, some heat escapes. But place that same conductor in a tight conduit with several others, or route it through insulation, and the heat has nowhere to go. The result? Elevated temperatures that slowly break down insulation, or in some cases, rapidly cause a fire. Electricians and inspectors use thermal cameras to check for hot spots. These devices don't just show faulty equipment. They reveal overloaded or poorly sized conductors glowing brighter than their neighbors. The rule is simple. Don't exceed what the wire can safely carry. Act 3. Ampacity and the NEC. Ampacity is the maximum continuous current a wire can carry without exceeding its temperature rating. These limits are defined by organizations like the National Fire Protection Association, NFPA, and NFPA 70, the National Electrical Code, NEC, NFPA 79. Wiring standards for industrial machinery. These codes list ampacities based on wire gauge, insulation type, temperature rating, installation method, in conduit, free air, underground, etc. Here are a few standard examples. Gauge, max amps, typical. From the NEC WA 14 AWG, 15 amps, 12 AWG, 20 amps, 10 AWG, 30 amps. For example, a 14-gauge copper wire with thermoplastic insulation is typically rated for 15 amps when run in conduit. If it's bundled with other wires or in a hot environment, that ampacity may be even lower. That's why proper wire selection and protection go hand in hand. And it's why overcurrent devices are selected not just based on the load, but based on what the wire can safely handle. Wrap up. Overcurrent protection isn't just about saving a motor or preventing a breaker trip. It's about preventing your wires from becoming the ignition source for a fire. Next episode, we'll dive into one of the oldest and most reliable forms of protection, the fuse, and we'll answer a critical design question. Does it matter where the fuse goes in the circuit? Spoiler, it absolutely does. Like, comment, and share this episode to help more learners stay safe and spark smart thinking.